All right. Today we're going through the last exercise of the unit. It's optimization, and this is quite a challenging exercise, but I want to break it down into two skills. The first skill is going to be finding the equation. Okay, so a lot of the questions in the textbook, they don't provide you with any equation. They want you to develop it yourself, and that's easily the most challenging part of this exercise. And then the next part is going to be finding the optimal solution. Okay, so a bit more on that in a moment. Now, when we present this to you in a test situation, we're always going to say, show that the equation is this. Show that the equation is this, which means you're given the equation and you need to develop an argument as to why that is the case. So then you're not penalised here if you can't get the first part. Okay? So finding the equation is going to be tricky. Finding the optimal solution, hopefully we're not too bad with that. Let's get straight into the exercise, and I'm going to point out the different skills as we're going through it. So we have, when a manufacturer makes X TVs per day, the profit is given by this equation. So the profit they're going to make is on the y-axis, the number of TVs they're going to make is on the x-axis. And what it's saying is there's some maximum amount of profit they can achieve. It could be because as you make more TVs, your equipment starts to deteriorate, you need to maintain it, or maybe you start paying your workers overtime, so it's not profitable to just make more. There's some optimal amount. When we're talking about the optimal solution, it means the most economic. It's going to make you the most profit, or it's going to cost you the minimum amount of money, and so forth. So we can see, if I just sketch the graph of this function, we can see the optimal solution. It's that local max, all right? And you can even G-solve that from your calculator. So if you're given the equation, you can literally just G-solve the optimal solution, all right? Now in a test, we're not going to accept that, all right? Because it's going to say very specifically, using calculus methods, find the optimal solution. So here, if we think about our two processes, step one says find the equation. We don't need to find it here because we're given an equation. So we're not being tested on that one here. Here we're going to find the optimal solution, and we're going to do that using calculus methods. Well, we know that local max and local min, they occur when the first derivative is equal to 0. So that means we're going to take our function, which is minus 0.022x squared plus 11x, take 720, and we're going to find the values, we're going to find the first derivative. So here's what we're going to say, optimal solution when p dash of x is 0. So we're going to find p dash of x. Fortunately, this is a pretty easy one to do. It's a quadratic. So just applying the power rule. And then we're solving that. And we get 250. Okay, so the optimal solution occurs when we make 250 TVs. So it says, using calculus methods, find the number of TVs that provide the maximum profit and what the maximum profit is. So it's saying, when you make 250 TVs, what is the profit? All right, and the way we're going to get that is by putting that number, 250, back into the original function. Remember, this is the profit function. P of x is the profit function. P dash tells you the rate at which profit changes. So we're finding P of 250, and we can get it straight from our graph, 655. And I think we're not told the unit, so that's a bit clumsy of me. We'll just say the unit is dollars. $655. Very good, first one. All right, on to number 2. We've got a farmer wants to build a duck enclosure against an old shed. So he's got a shed here, and he's going to build a fence, a rectangular fence around it, and he's got 200 meters of fencing to use. Find the dimensions that provide the maximum area for the ducks. Okay, so here we're not given an equation, are we? We need to find the equation. And most of the questions in the textbook are like this. They make you find the equation first, which can be a little bit challenging. All right, so we're given the diagram though, and that's going to be very useful. All right, so we want to provide the maximum area of this rectangular duck enclosure. So based on the dimensions we're provided with, what is the area? We can write it like this: the area with regards to x, okay, the function of area with regards to x is equal to length times width, right? For a rectangle, x times 200, take 2x. And so our area function is this: 200x, take 2x squared. Now we want to find the optimal solution. Optimal solution when a dash of x is 0. So a dash of x will be 200, take 4x. Okay, 200 take 4x. And let's read it carefully. Make sure we answer the question. Find the dimensions that provide the maximum area. So it wants us to state what are the dimensions of this duck enclosure. So we'll say something like, therefore duck enclosure is, well, the length is going to be 50 by, and what's the width? 200 take away 2 times 50. That's 200 take 100, 50 meters by 100 meters. So it's not asking for the area, it's asking for the dimensions. Make sure you answer the question clearly. So this one, hopefully not too challenging, finding that area there, finding that function. Things to point out, we've got 200 meters of fencing, right? So you can see if we add up all of the sides of this rectangle, it will equal 200. So that's how they've generated that diagram and so forth. Okay, let's move on to the third one. And we've got, in an attempt to be more environmentally friendly, Coca-Cola have decided to try and minimise the amount of aluminium used to make a can. The new can is still going to have a volume of 375 meters. If R is the radius of the can, show that the height is given by H equals 375 on pi r squared. All right, so firstly, if we ever expect you to make one of these geometric arguments, we're going to provide you with the formulas that you need. So for example, the volume of a cylinder is pi r squared H. All right, so we've got pi r squared H, that's the volume. And for part A, we've got R is the radius of the can, the volume is 375, and it says show that H is this. Well, if we divide both sides by pi r squared, all right, this will cancel, we're going to have H over here and 375 on pi r squared here. So that's the first part. All right, we've demonstrated that H is 375 on pi r squared. Now, hence, show that the amount of aluminium used is given by this equation, the amount of aluminium. So if you're using aluminium to make a can, maybe one piece of paper, and all right, we're going to need aluminium at the bottom, aluminium at the top, and aluminium the whole way around. So the surface area, we can call this the surface area of aluminium required, is equal to the top All right. Now the area at the top is a circle. The area of a circle is pi r squared. And we also have the area of the bottom, right? And that's going to be the same, pi r squared. So the surface area then is going to be 2 lots of pi r squared. Okay? Plus 2 lots of pi r squared, plus the area of this distance around the outside. And this distance around the outside, you think, how do we get what that is? This area around the outside, sorry. One way to think about it is, let's chop it, get some scissors out and chop it down the middle there, and it's just a rectangle. Okay? What is, this is the height of the cylinder. What is this one? It's the circumference of the circle. Very good. So it's the circumference of the circle. So we look at the formulas we've used here so far. We've got the volume of the cylinder, we've got the area of the circle, and we've got the circumference of the circle, 2 pi r. So anytime, I wouldn't really expect you to remember them. If I was going to ask this question in the test situation, I would say it's going to be area of a circle, circumference of a circle, and I would include formulas. All right, so yes, we established that this part here is a rectangle, and the area of the rectangle is 2 pi r times h. All right, 2 pi r is that circumference of the circle, and then h is the height of the cylinder. All right, so that's going to be the surface area of a cylinder. That's the formula for the surface area of a cylinder. And we've derived that just from the area of a circle, the circumference of a circle, and the area of a rectangle. That's how we've arrived at that. Okay, now, we've got 2 variables here. We've got r, the radius of the cylinder, and we've got h. H is the height of the cylinder. And if you've drawn a cylinder, you can vary those, right? You can change the radius and make it bigger. You can change the height and make it longer. All right. So we want to rearrange this so that we've only got one variable we're dealing with, and that was the purpose of the first part. Look, we've isolated h, and we can express h in terms of r. So now we're going to substitute that in here. We're going to have 2 pi r squared plus 2 pi r multiplied by 375 on pi r squared. All right, and then we've just got to simplify that. So here we've got r at the top and r squared at the bottom, so that will cancel and that power will cancel. We've got pi at the top and pi at the bottom, so that will cancel. And so what we're going to be left with, 2 times 375 is 750 on top of r. All right, and that's what it requires us to show, right? 2 pi r squared plus 750 on top of r. Okay, so let me check where we're up to. Show that the amount of aluminium used for area with regards to r. So I've just written that as surface area, but we can call it the area of aluminium used with regards to the radius is this equation. Turn the page. Using calculus methods, find the radius, height, and surface area. All right, so now that we've developed the equation, we can G-solve. We want the optimal solution here, and they're saying they want to be more, what was the claim? They want to be more environmentally friendly. They want to use less waste. They want to use less, they want to use the minimum amount of aluminium. So we'd be G-solving them in, we could get that from the graph. Let's use the calculus methods. So, optimal solution when A dash of R is 0. So let's go for, well, firstly, A of R is this. I'm going to express it in a form ready to differentiate. Alright, so all I did there was move the R here to the top, and now we'll differentiate all in one step. Keep going. these. Yeah, there, and that's why I've taken them to the bottom. Can't see it, yeah. Okay, very good. So we're there. So we've differentiated it, and then I've just put it in a sort of friendly form. I've moved that to the bottom. And now what we're going to do is we want to solve this for R. And fortunately, we've got a pretty cool tactic here. What we're going to do is we want to get rid of that denominator. So I'm going to start by multiplying both sides by R squared. Okay, so 0 times R squared. That side just stays as 0. Over here, it's going to distribute, right? So we're going to have 4 pi R to the power of 3. And then over here, we would have R squared at the top, R squared at the bottom. So we're just left with 750. Okay, and now we've only got the variable in one term, so we can shove the 750 across. Divide both sides by 4 pi. Alright. And then we perform the cube root of both sides. What we're doing when we cube root, alright, so we're going like this, right? Cube root equals the cube root of 750 on 4 pi. Now, one of the things we're learning when we talk about index laws is the square root of A is A to the power of a half. The cubed root of A is A to the power of a third. And so what we're doing is we're putting both sides to the power of a third. All right, and then you can see, well, 3 times a third leaves you with 1. All right, sorry, that should just say R. Leaves you with 1, so we've got R to the power of 1. All right, is that clear? Yeah, all right, cool. So that's the R value that provides us with the optimal solution, and there we've found it exactly. And sometimes we will ask for it exactly, and that's one of the ways that we can stop you from just G solving that max. All right, if we ask for it exactly, it means you have to go through and find the solution to this using those algebraic techniques. Okay, so now that we've found the value of R, let's answer the question. Find the radius, height, and surface area. So you can put this in your calculator and evaluate it to a few significant figures. That's going to be the radius. I'm going to spend a bit of time here just typing out the equation, which is 2 pi x squared plus 2 pi plus 2 plus 750 of x. 2 pi x squared plus 750 of x. Alright, and I've got to restrict my domain a fair bit. Okay, that's looking good. So we can see the minimum solution of there and there. Now, what is this a graph of? Well, this is the graph of the surface area function, right? On the x-axis, I've got the radius, all right? So that means when you evaluate this value, here's what it becomes, 3.908 as 3 significant figures, 3.91. And what's on the y-axis? Surface area. So that means the area of aluminium used. Is 287, so we'll round it to 288. 3.91 centimetres. Now, let's talk about how I've arrived at centimetres. That might be a little bit unclear. Here we have 375 millilitres as the volume, and 1 millilitre is a centimetre cubed. All right, centimetre cubed. And so because our volume is in centimetres cubed, our dimensions are going to be in centimetres. And that's this. So we've got surface area, we've got the radius. One more thing it asked for was the height. Well, here's the height here, right? The height is 375 divided by pi r squared. So then the height is going to be 375 divided by pi times 3.91 squared. All right, so we can just evaluate that quickly. 375 divided by 5. I've got 7.807, 7.81. Okay, so we've answered the question, right? 7.81 centimetres. So the amount of area used, 288 centimetres squared. Here's the height of the new can. Here's the radius of the new can. We found the optimal solution.
It's a very small can.
It's a small can, yeah. Well, that's the radius of it, which is cool. So if you think...
Oh no, the height.
The height of it.
7.817.
Yeah, it's like a baked beans or something. Yeah. All right, so this is a challenging exercise. So what I'm going to do, I might let you guys tackle it for a little bit, and then maybe in 10 or 15 minutes or so, I might just start talking about this part of it, okay? So hopefully, the finding the optimal solution, we are pretty okay with. Now there is one thing that we do need to include here that I haven't shown you. And that is, it's not really enough to just say that this is the optimal solution. What we need as well is a sign diagram, all right, with the optimal solution drawn on it. And what we're showing you is that that's a local min, right? So we know it's a local min because we can see that from the graph, right? And sign diagram just supports the fact that this is the most economic solution in the context of that problem. So use a sign diagram to accompany your answer. All right, so I'll stop there, okay? And I'll get you to have a bit of a wrestle with the first few.